Hello, everybody. In this episode, we will continue from last time. In last episode, we saw what is the definition of exact first order differential equation. So, a quick reminder, an exact first order differential equation can be always written this way here, right? M plus ny prime equal to 0, which is the same thing to say I can also write as m dx plus n dy equal to 0. You can simply replace y prime by dy over dx, right? And then you multiply by dx if you want. But typically we're going to write like this. And this differential equation is called exact if there exists a two variable function phi, which we're typically going to call it phi, so that the partial of phi with respect to x is equal to m. That's the subscript notation for the partial derivative. I hope you remember. It's the same thing. So they both means the same. And similarly, the partial derivative of phi with respect to y is equal to n. And in that case, the solution of the differential equation is given by phi equal to c, where c is the parameter. C can be any real number, negative infinity to infinity. That is the solution of a exact differential equation. So there are a couple of questions which we're trying to answer in this episode. Number one, how I know that this is a solution? What is the proof? So we'll do that first. And then we're going to look at how to check a given differential equation is exact or not. So let's start with the solution, how we know that this is a solution. A very simple and quick proof, and it actually also reminds us the chain rule for multivariable function. So let's think about our function phi. So this function phi, right? This function phi, right now, this function phi, as it looks like, is a function of x and y, correct? But remember, y itself is a function of x. So I can actually rewrite this x comma y, but y itself is a function of x. So we should not forget that. So at the end of the day, we can think this whole thing phi as some function of x, because y itself as a function of x. That's the solution of the differential equation. Y of x is the solution of the differential equation, right? So in this way, you can actually think the phi is actually at the end of the day as a function of x. So let's think about what will be the derivative of phi with respect to x when we're thinking phi as a single variable function. We are thinking all the y itself is a function of x. So in place of y is actually some function of x, which is the solution of this differential equation. So we're thinking phi as a function of x alone. So in that sense, we can talk about what is the derivative of phi with respect to x, right? What is that? Okay, so let's come back to this equation here. Let's try to find that. So let's take the derivative of both sides with respect to x. So let's take the derivative of both sides with respect to x. Again, on the left hand side, we're thinking phi as a function of x only, and my y is itself as a function of x. So my y is actually y of x. So in that sense, phi is a function of x. So we're using d notation instead of delta. But to figure this one out, that's actually a chain rule for the multivariable function. So if you remember how we do the chain rule, you start with the function phi. In this case, phi depends on x and y. but y itself depends on x. And of course, x itself depends on x if you want. Okay. So if you think about this diagram, each path you have a name. So this path, the partial of phi with respect to x. This one, we're taking partial of phi with respect to y. Here, I'm taking the derivative of y with respect to x. In this case, we're thinking y as a function of x. So it's just a one variable function. So we can use the d notation, not delta. Here, the answer is 1 because the partial, the derivative of x with respect to x is 1. So to go from phi to x, I have two paths. One in this way, and the other one is this way. So the chain rule, if I apply the chain rule, so in this side, if I apply the chain rule, is this red path, which is partial of phi with respect to x multiplied by 1, plus the purple path, the partial of phi with respect to y multiplied by dy dx. So that's the purple path. And that's supposed to be equal to this one, which is 0. The derivative of c is a 0. That's a constant. Now remember, my phi is not any phi. Phi satisfies this equation. The partial of phi with respect to x is m, and the partial of phi with respect to y is n. So let's substitute that here. So this one, the partial of phi with respect to x, that's m, plus this one is n, and my dy dx is exactly y prime equal to 0. So look at here. So my solution y satisfy this differential equation. That's exactly the question. That's our differential equation. So this solution, when I take the derivative, it satisfies this differential equation. My y prime satisfy this differential equation. Is true. This equation is true. And that shows that this equation, this implicit equation, represent the solution of this differential equation because y satisfy this differential equation. Very simple proof, but yet is very important to understand. Now, if I give you a arbitrary linear first order differential equation in this format, how you know it is exact or not, right? So if I give you a first order differential equation, right? How you know that this is exact? How to know it is exact? So what is the definition of exact? Exact means there exists a function phi so that the partial of phi with respect to x, I will get m, and the partial of phi with respect to y, I get n. So let's first assume that it is exact. So such a phi exists. If it is exact, by definition, such a phi exists. So I have these two equations here. So let's do some simple algebra. So from here, from the first equation, let's take the derivative of both sides with respect to x. So let's take the partial derivative with, let's take the partial derivative with respect to y of both sides. So let's take the partial derivative with respect to y. Let's do that. So I'm taking partial derivative of both sides with respect to y. So the left hand side, if I take the partial derivative with respect to y, that is exactly the second partial of phi, first with respect to x and then with respect to y. And for here is simply the partial derivative of m with respect to y. For the second equation, let's take the partial derivative of both sides with respect to x. So partial derivative of both sides with respect to x. So this side, the left hand side, I end up with the second partial of phi, first with respect to y and then with respect to x. And when I take the partial derivative with respect to x, this is simply partial derivative of n with respect to x. Now we're going to assume all the partial derivative of phi and all the partial derivative of m and n is going to be continuous in some region. So from the mixed derivative theorem from calculus 3, you know that the order of the partial derivative does not matter. So this two, if I take the first with partial derivative with respect to x and then with respect to y, I will get the same answer if I first take the partial with respect to y and then with respect to x. So the order does not matter. So this two is actually same according to the mixed derivative theorem that you learned in calculus 3. So if those two are same, of course these two must be also same. They also has to be equal to each other. In other words, the partial of m with respect to y should be equal to the partial of n with respect to x. And in fact, it can be shown that you can actually go other way around. If the partial of m with respect to y is equal to the partial of n with respect to x, and they are continuous in some rectangle or in some open interval, it can be shown that you can actually go back and such a phi exists. You can actually define a phi. You can actually define a phi which satisfies these two equations. That proof is a little bit complicated. It's on your book, so I will avoid that proof in this. But this actually you can actually go backward and recover phi. So the conclusion is that that is how you check. Remember, m and n is given in the question. So remember, in the question, you have the m and n. Remember, the question is m plus ny prime equal to 0. So m and n is given in the question. So you can easily check this one. So if it is true, then the differential equation is exact. And if it is false, then the differential equation is not exact. So if this equation is false, then you cannot find potential function. Sorry, I forgot to tell you. This phi is actually sometimes called a potential function. So such a function phi does not exist. So if this equation is false, then you stop. You cannot find the phi. So you cannot use this method. You have to use some other method. Maybe it is linear, or maybe it is separable, and there are several other methods that we're going to learn later on, but it is not exact. And if it is true, then yes, you can find the phi, and you can go ahead and try to find the phi. So how we are going to find the phi? That we're going to look at in the next episode. Thank you very much. And do not forget, you can do it. Yes, you can do it.